We're moving on into chapter 14, and we're going to start talking about electricity. Now, in all fairness, many people find the study of electricity to be quite interesting, actually. It can illuminate a lot of stuff. It can really invigorate you. You feel quite powerful about it. Although some people do find it a little shocking. Yeah, wasn't going to pass it up. All right. Now, when we talk about electricity, we need to kind of start with a basic idea of what this is before we start diving into how do we turn on lights or how do we power an iPhone. So let's consider the case that perhaps you've had before, where you've put your finger near a door and been zapped by something. That something that you've been zapped by is a good example of an electrical discharge. Something went between your finger and the door, and it hurt like the dickens. So our goal is to try to think about what's happening there, and hopefully we can come back to this and it'll make sense when we get to it in class. So to start, let's come up with a simple experiment. Let's say that I have a balloon. Here is a balloon. Balloon probably has two L's. I don't know how to spell things. It's a balloon, you can see because it's balloon shaped, and a piece of wool. What I'm going to do is rub the wool on the balloon. If I do this, what's going to happen, the balloon is going to become slightly attracted to the wool, and the wool is going to become slightly attracted to the balloon. This is going to be more noticeable in the balloon because it's going to be hanging there, and it's going to start to like creep up and angle towards the wool a little bit. And you might think, this is a little weird. Or you might think, this is like every time I've tried to pull on something and like been hit by static cling. Because that's kind of what's happening. Something is happening when we rub these two objects together. So let's say I take two balloons prepared in the same way, and I bring them together. What I'm going to find is that they repel each other a little bit. And so you might think, all right, that's a little odd. So clearly something is going on here. We've got, for my two balloons, there is some tension from the strings. There is some weight on them because of gravity. But then there is some outward force here, and this is the thing that's interesting to us. This is from the other balloon, so it's some force on balloon. I've committed to it by other balloon, and then this would be the third law pair, so it's the force on other balloon by balloon. And so now what's really interesting, if I bring these balloons closer together, so if I move these bits of it closer together up here, the balloons, they're going to push even further out. So, all right, so there's something's happened. The balloons have been what I'm going to call charged. So we want to try to explain this with some model of electricity. And apparently, if they're charged the same way, they repel each other. And furthermore, if they get closer, they repel each other more. Now, being a clever individual and having apparently too many random fabrics and materials around, I can also prepare a balloon. So this one has been rubbed, as we did before, with wool, but this other one I'm going to rub with plastic wrap. And that's why it's blue, because plastic wrap. If I do this, I find that the balloons attract to each other. And now, if I went back and did this with two blue balloons, I would have found the same thing. If I charge them up with plastic wrap, they still don't like each other, but a plastic wrap charged balloon seems to be attracted to a wool charged balloon. Now, we could spend a whole lot of time charging up some objects and playing with it, but let's summarize a quick couple of findings that we might discover if we did the same thing. We might also find that my balloon, once it's charged up, is going to be attracted to pretty much almost literally everything if it's charged sufficiently. I might also find, if I rub it more with the wool or with the plastic wrap, that it seems to be more charged. So by that I mean I might feel more of like a weird tingly thing when I put my hand to it, or I might find that it more readily attracts or repels from things, or I might find that it accidentally zaps me more often if it's been rubbed more with the wool or with the plastic wrap. I might also find if I bring it near something that's kind of metalish, it seems to attract to it more than if I brought it near just like, the wall that's made of wood or something like that. So, putting all these things together, I'm going to make these 7 claims here. I'm going to say that, materials rubbed against each other acquire something that we're going to call electric charge. This is something new. It's a physical property kind of like mass. So material has an electric charge. Not because of its material, but because of what's happened to it. So, I could have an aluminum desk. The aluminum desk has some mass, not because it's made of aluminum, but because of how much aluminum it has. I could have a computer, and the computer could have an electric charge because maybe it was rubbed with a piece of wool or something. Well, that'd be kind of weird. We seem to have this case where two objects with the same type of charge, so two objects that were charged the same way, repel each other. Similarly, two objects with opposite types of charge, this idea of opposite is new. So we're saying that we found two ways of charging things. So two ways where they both repelled, so both the red balloons and the blue balloons that had been charged by wool and plastic wrap. When it was two red balloons, they repelled, and I claimed if it was two blue balloons, they'd repel. But I'm saying that red balloon and that blue balloon, they seem to be attracted. So I seem to have two types of charge going on here. So two objects made of different materials rubbed against each other require opposite charges. We saw that because the balloon, way back at the beginning, is attracted to the wool. So something happened to charge the wool that also charged the balloon. The magnitude of the force that the charged objects exert on each other increases when the distance between the two objects decreases. I bring them closer, I see more repulsion, or I see more attraction, although the more attraction is tough because you bring them closer, they get more attracted, so they want to go closer, so they get more, so they're closer, so they're more attracted, so they get closer, so it's really tough to measure. Sometimes more vigorous rubbing leads to a greater force exerted by the rubbed objects on each other. So if you rub more, you seem to transfer more charge, you seem to charge them more. And uncharged objects are attracted to both positively and negatively charged objects. We've already kind of jumped ahead here a little bit. Instead of just calling them opposites, we're going to take this idea that one is a positive charge, one is a negative charge. And metal objects seem interesting. We're going to return to that in a little bit. So building on this, by convention, when I rub wool on a balloon, the balloon is going to pick up a negative charge, and the wool is going to pick up a positive charge. And the way we think of this, all matter is made up of charged elements. We know a little bit about atomic structure. So we know we've got protons and electrons, and they're not really spread out like this, but it serves to help illustrate the point. So when I rub these together, if this is going to become a negative charge, that means that some of these electrons are zipping over here during this process. So now I've got some extra electrons here, and I have lost some electrons, and apparently half of the wool, over here. 4. Darn it, I liked that wool. But, so, come on. Hello? That was challenging. Okay. If I look at this now, I see that there is a net negative charge on this balloon. There are more electrons than I was expecting. I've got an excess of electrons. If I look over here, I see I have a deficit of electrons on the wool. So that's why we're going to say that the balloon has a net negative charge, or is negatively charged, and the wool has a net positive charge, or is positively charged. We'll come back. When you take chemistry, you'll get much more into atomic models, and we'll talk about it a little maybe. But for now, we just need this basic idea that we have, small electrons are the thing that we're really thinking about as being the mobile charges in these cases. Now, the one thing that we got here, all matter is made of charged particles, but not all matter responds to charge the same way. We saw a slight difference in how metal responded as opposed to wood. So we're going to say there are two major groups of materials, conductors and insulators. And we're going to separate these based on how they respond to charge. So conductors are going to be mostly metals, although sometimes certain solutions might be a conductor, sometimes even air can be a conductor. They're going to be characterized by having free electrons, and by this I mean electrons that are loosely or not bound to the kind of broad structure of the material. This is going to lead to global rearrangement of these electrons when an external charge comes by. So we'll talk about that more. Insulators, on the other hand, most notably going to be like plastics and glass, or basically everything that's not a metal. These are sometimes going to be called dielectrics, specifically in your book. These are going to be characterized by more tightly bound electrons, localized electrons, and this is going to lead to a local rearrangement of charge. So consider this copper tube. It's a very nice copper tube. If I bring a positive charge near this copper tube, or a positively charged object, what's going to happen is that all of the positive charge is going to want to migrate away. Now, it's not that the positive charge really moves away so much as the fact that the negative charge, what we're thinking of as being the mobile charge in this case, these electrons, is going to swim over to the left side of this tube. And every electron that leaves the right side to come to the left side leaves behind a positive charge somewhere. So I wind up with a net positive charge on the right and a net negative charge on the left. So this can happen, even if I have multiple metal objects, multiple conductors next to each other. They're going to move as far as they can. That's what we mean by this global rearrangement of charge. Now, if instead I had, let's say, a plastic cup, and I brought, it's really being fussy today, again, a positive charge near this, what I'm going to see instead are the formation of what we're going to call dipoles. Dipoles because they have two poles. The positives are going to move a little bit to the right, and the negatives a little to the left. And so, I'm exaggerating this effect so that we have a chance of seeing it, but each one of these little configurations here is what we'd call a dipole, something that has a negative side and a positive side. So this is what we mean by a local rearrangement of charge. One way to think of this, imagine you have one of those like kid backpack things. So, the discrete way of putting a child on a leash. Put aside whether that's a good thing or a bad thing. So that has your electron, the child, tightly bound to the nucleus, the parent or whoever has control of the backpack. The external charge might be a toy store or a candy store or something that attracts the kid's attention, so the kid runs towards it. In the case of a plastic, of an insulator, of a dielectric, you have that leash. The kid can only go so far. So you get spread out where the kid wants to go towards the charge, the parent maybe not so much, they're bound in place. So you get that spread out bit. In the case of a conductor like copper, the leash breaks, kid goes flying, just, smushes their face up against the glass of the store. They go as far as they can go. So no leash, conductor, functioning leash, plastics. Now, we're going to build on this model as we go on, trying to think more about what exactly it means for these charges to be interacting, how big this force is, how it depends on separation. For now, our big idea that we want to hold on to is this split between conductors and insulators and these basic ideas of how charges interact with each other. This is kind of the material from sections 14, 1, 2, and 3 in the book, and look forward to more in class.